Okay, let's dive in. Imagine the universe is like this giant balloon expanding.
Right.
And for the longest time, we figured, gravity must be acting like a brake, slowing that expansion down.
That was the standard picture. Absolutely. Made perfect sense.
But then, bam, late 90s, scientists are looking at these really distant exploding stars, supernovae.
Supernovae, yes. They're like standard candles for measuring cosmic distances.
And they found the expansion wasn't slowing at all, it was speeding up.
A completely shocking discovery at the time. It turned cosmology on its head.
And that acceleration, that's apparently down to this mysterious thing we've labeled dark energy.
Dark energy. The placeholder name for whatever is causing this cosmic push.
And it makes up something like 68% of the entire universe's energy density. Think about that. Most of the cosmos.
It's truly humbling. The vast majority of the universe is composed of something we just don't have a solid explanation for yet.
It's like that balloon analogy. Again, it's not just inflating, it's inflating faster and faster over time.
Exactly. And that acceleration implies some kind of fundamental force or energy property of space itself that we hadn't accounted for.
So that's the big mystery. And the mission for this deep dive is to look at a really exciting new development, a new attempt to actually get a better grip on this cosmic speed demon.
Okay.
We've got some great material detailing a significant breakthrough, actually, a new method, yielding some, frankly, seriously impressive results.
And getting those results is crucial because understanding dark energy isn't just, an academic exercise.
Right, it's fundamental.
It tells us about the fabric of the universe, its history, its ultimate fate. Is space just inherently pushing itself apart? That's the cosmological constant idea.
Einstein's idea originally, right? Though he later called it his biggest blunder.
He did, although now it seems remarkably prescient. Or maybe dark energy is something dynamic. A field that changes.
Like this thing called quintessence.
Quintessence is one possibility, yes.
Okay.
A field that evolves over cosmic time. Or it could be something completely outside our current physics.
Which is why new experimental approaches are so vital. And that brings us right to the core of our deep dive today.
Okay, what do we got?
It's a research paper just out in Nature Astronomy. It's titled Experimental Constraints on Symmetron Field with Magnetically Levitated Force Sensor.
Okay. Symmetron field. And a magnetically levitated sensor. That sounds
Precise.
extremely precise. That's the key. Researchers, primarily at Nanjing University, but working with folks from the University of Science and Technology of China and Zhejiang University.
A collaborative effort, then.
Definitely. They've developed this really cutting-edge new system and its purpose.
Yeah.
Measuring incredibly, unbelievably tiny forces.
Which you'd need if you're hunting for signs of new physics related to dark energy.
Exactly, because many of these alternative ideas, the ones beyond just a simple cosmological constant.
They often predict new forces, right? Very weak ones, maybe only acting over certain distances or in certain conditions, sometimes called fifth forces.
Fifth forces, yeah. Whispers, basically.
Yeah.
Forces so faint they're easily drowned out by, everything else. So you need an instrument that's exceptionally quiet, exceptionally sensitive to even have a chance of detecting them.
And that is precisely where this new system comes in, this magnetically levitated precision force sensor.
Magnetic levitation.
Yeah.
Yeah, so they're floating the sensing part.
Basically, yes. Think about trying to weigh, a feather on a regular scale in a shaky room. Impossible, right?
The vibrations would overwhelm any reading?
Exactly. So by using magnets to levitate the core part of their measuring device, they essentially cut out all those vibrations, all that mechanical noise, friction.
Creating an ultra-stable, ultra-quiet environment. Like putting the experiment in a perfect soundproof box, but for forces.
You got it. It isolates the sensor from the noisy world around it.
That magnetic levitation is clever. It bypasses a lot of the limitations you get with conventional setups, like cantilevers or torsion balances, where friction and physical contact are always issues.
And the result, according to the paper, is, it's staggering. They've improved the precision, the sensitivity of force measurement by 6 orders of magnitude.
6. So 1,000,000 times better.
1,000,000 times more sensitive. That's like going from barely seeing a candle flame a mile away to spotting a firefly.
Wow. Okay, that kind of leap doesn't happen often in experimental physics. That's huge.
It really is. And here's why it's so critical for dark energy research. This massive jump in precision opens up totally new territory.
It means they can now probe effects predicted by some of these more complex dark energy models effects that were simply too small, too weak to be detected before.
Right. theories that previously lived only on paper because we couldn't actually test them experimentally.
Now, with this millionfold improvement, those theories face a real experimental reckoning. We can start putting much tighter limits on them, or maybe even find evidence for them.
And the specific theory they targeted in this study is something called the symmetron theory.
Symmetron. Okay, what's the basic idea there? Without getting lost in the weeds.
Well, the gist is it proposes a new force field related to dark energy, but its strength isn't constant. It depends on the local density of matter.
Ah, so it behaves differently in different environments.
Kind of, yeah. In dense places, like here on Earth or inside a star, the theory suggests this force gets suppressed or screened. It hides.
Which would explain why we haven't easily detected it in standard lab experiments or within the solar system?
Exactly. But out in the vast emptiness of intergalactic space where matter is very sparse.
The force could become much stronger unscreened.
That's the idea. Strong enough, potentially, to drive the accelerating expansion of the universe.
Interesting. So it provides a mechanism for dark energy to be dynamic and to interact with matter, but in a way that's subtle, where matter is dense.
Right. And this interaction, even if weak locally, might just be detectable with an ultra-sensitive experiment like this new one.
The theory presumably has some free parameters, right? Like
Yeah.
knobs you can tune that determine the strength and range of this symmetron force.
It does, and that's what this experiment is designed to constrain, to figure out what settings on those knobs are still allowed by reality and which ones aren't.
So they're basically testing, if a symmetron force exists, how strong or weak could it possibly be, given what we can measure?
Precisely. And the paper includes a figure, figure 2, that really paints a clear picture of their achievement.
Okay, what does it show?
It shows graphs mapping out this parameter space, all the possible combinations of strength and range for the symmetron interaction. And there are shaded regions showing the combinations already ruled out by previous experiments.
Standard practice in this kind of work, you map out the excluded territory.
But the key thing is the new region they've managed to explore and rule out, it's shown in red on their graph.
And because their experiment is so much more sensitive.
That red region represents a significant chunk of previously unexplored possibilities for the symmetron theory. They've substantially tightened the constraints.
So they've effectively shrunk the space where this particular theory could be hiding. Every time you do that, you're learning something fundamental.
Absolutely. It's like detective work on a cosmic scale, as you said earlier, crossing potential characteristics off the list. It helps narrow down the search for what dark energy actually is.
Even ruling theories out is progress. Big progress, in fact.
Definitely. And it's worth pointing out again, this wasn't a lone genius effort. This involved physicists, astronomers.
Across different fields and institutions. You mentioned Nanjing University, USTC, Zhejiang University.
That's right. The paper lists co-first authors Dr. Perrin Yin, Shanghui Zhu, Qinan Tian, suggesting equal key contributions at that level.
And the senior researchers overseeing it.
Co-corresponding authors listed are Dr. Xiaochen Lin, Professor Pu Huang, and Professor John He from NJU, and academician Zhangfeng Du. It really highlights that tackling these huge questions needs collaboration.
That interdisciplinary approach is often essential. You need the people who understand the cosmological theories, the people who are experts in building incredibly precise measurement devices.
The atomic physicists, maybe. It all comes together.
It's often at the intersection of fields that these kinds of breakthroughs happen. Building something this sensitive requires expertise from many different areas.
So let's sort of wrap up the core finding here.
Okay.
The major achievement is this incredible leap, 6 orders of magnitude, 1,000,000 times better in measuring tiny forces using this new magnetically levitated system.
A technical feat that translates directly into scientific insight.
Yes, because that leap allowed this team to perform the most sensitive tests yet of a specific dark energy model called the symmetron theory.
And by doing so, they've ruled out a significant portion of the possible ways that theory could manifest itself.
Exactly. It's a concrete step forward in that massive quest to figure out what's driving 68% of the universe.
It really underscores how developing better tools, better ways to measure things, pushes the frontiers of fundamental science.
It's not always just about the big idea. Sometimes it's about having the ability to actually test the idea.
Precisely. Pushing the limits of measurement technology opens up windows onto potentially new physics.
Okay, so let's leave our listeners with something to chew on. A final thought.
All right.
Given this remarkable jump, this 1,000,000-fold improvement in measuring force, what else could become accessible? What other maybe fundamental forces or cosmic puzzles, things we haven't even thought of, properly yet, might we be able to investigate with similar leaps in technology?
Hmm, that's a great question. If you can measure force with this precision, perhaps subtle deviations from gravity or searches for other hypothetical particles that mediate new forces.
Right. Think about it. If this level of accuracy is achievable for force, what other fundamental quantities could we measure with similar breakthroughs? Time, distance, something else.
It really makes you wonder how these technological advancements, seemingly focused on one specific problem, could cascade and completely revolutionize our view of the universe in unexpected ways.
What hidden aspects might finally come into focus? It's exciting to think about.